Okay, yeah. So I'd like to thank the speaker for inviting me, especially also for inviting me a year in advance, so I had time to prepare new research. So a lot of this is research that I thought I ought to do in order to come here and not present the same things I've been saying over and over again. So anyway, so I'll be talking about financial applications of random matrix theory, but I think what I'm going to say applies to any field with big data. So where you need to measure sample covariance matrices using data. Okay. So the outline of my talk is as follows. So the first part is what have sort of essentially been. Well, okay. So the first part of the talk is really about.
The pointer not working, or
the point. Yeah, the pointer. Oh yeah, it's kind of on and off.
I can get you another one if you like.
Well, it's fine. Yeah. No, I'll be fine. Yeah. Okay.
It's not working?
Well, it's on and off, so.
It's running out of juice.
Yeah. Okay. Yeah. Anyway, so the first part is essentially what I've been saying since 1998 about eigenvalues of sample covariance matrices and why it's relevant to finance. And the rest of the talk is more recent work I've been doing, trying to go beyond the simple ad hoc framework that for cleaning matrices that I'm going to present. Okay. So this leads to so basically we write a Bayesian framework, which is just a matrix models. We try to solve it by perturbation theory. We can get at least to one loop. We try to do an eigenvalue saddle point, but we're stuck with the what we call in physics the Itzuk-Zuber integral, so the HCIZ integral. And we need to make some brutal approximation in order to do something out of this. We found a numerical method that actually works quite well, and probably in practice is basically all you need. But it's very important to understand the theory behind when you're doing something. And so I'll finish with some conclusion. Okay. So what is the problem I'm looking at? So you don't need to know anything about finance. You can think of it as just an optimization problem where you have coordinated random variables that you can observe. So they're n of m, and n is a large number. I've normalized them to have 0 mean unit variance because those don't really matter in the problem. And I want to find a linear combination of these variables with minimum variance. Of course, if I don't have any constraints, yeah. Okay. If I don't have any constraints, then the minimum the vector with minimum variance is a 0 vector. But I put a linear constraint. I want the gain, which is just a okay. Yep. Okay. Where's the pointer? Here. Okay. So this is a linear constraint. I want this gain, which is just the weight vector times some fixed vector, to be equal to some constant. So I'm looking for those weight w's that minimize the variance. And this is a very simple optimization problem. You just use the Lagrange multiplier, and you find that the optimal weights are given by the inverse matrix, the inverse covariance matrix applied to this fixed vector g, and then there's some normalization in order to satisfy the constraint. So this was done by Markowitz. He had a Nobel Prize for this, but it's quite important in finance. But the problem with this framework is that you need to inverse the sample covariance matrix. So the sample covariance matrix, if you think of its eigenvalues, this will put a small weight, so 1 over the eigenvalues of the sample covariance matrix. So it puts a lot of weight on small eigenvalues of the sample covariance matrix. And that could be a problem. So first, let's look at those sample covariance matrix, what they look like. So this is real data. This is actually a graph from 1998, but we've done it many times before, and it still looks like that. So what is this? So variances are normalized to 1. So so I have data. All the variances are 1. So the trace of my matrix should be equal to 406. So the average eigenvalue should be 1. Okay. So I have one very big one, which is in this data set was close to 60. This thing fluctuates. It could be as big as 100. So it's essentially almost 25% of n. So it's a macroscopic mode called the market mode. So it just says that all stocks tend to move together. Okay. So this is definitely an important signal in our data. And then some more eigenvalues here that are between say 4 and 10, which also have clear economical meaning. Things like during the financial crisis, for instance, it was banks going down and the rest of all of their companies going up, or in the tech bubble, it was tech company doing one thing and other companies doing something else. Of course, these are eigenmodes, so they're given that this vector is essentially everybody moving together, all of these have to be orthogonal so it's always relative motion. Okay, but what I want to show is that.
Is this a density of states for this?
Yeah, exactly. This is for one matrix, for one empirical matrix. So it's essentially a histogram. You just use little Gaussians on for individual values. So here you see there's only one eigenvalue, but in the bulk we just smooth it out with little Gaussians. So it's a density of state for a single matrix, and you see that there's a big bulk of eigenvalues close to 1. That when we first look at this, we wonder, is this signal or is this noise? And then we found out about the work of Marcenko and Pastur, and they tell us that this is essentially measurement noise. So what Marcenko and Pastur solved, this is a formulation by Polish physicist Burda and co-author I find useful, but it's essentially, you can get the same results directly from the paper from 1967 of Marcenko and Pastur, which is given a true covariance matrix, you measure a sample covariance matrix using t data points where the ratio of the size of the matrix and the number of data points is a number q, which is finite, which is between 0 and 1. Well, actually, it can actually be bigger than 1, but I won't be considered that case. So let's say I always have more data points than I have variables. So q is between 0 and 1. What is the asymptotic eigenvalue distribution in the limit of n and t going to infinity with q fixed? And it's given by this equation, which is the resolvent of the true matrix is related to the resolvent of the E for empirical for the sample covariance matrix by this implicit transformation. So this is easy to solve numerically with complex numbers. So that's why I like this formulation. But okay, and of course, what's known as the Marcenko-Pastur distribution is the case when the true covariance matrix is the identity, then you can do this very explicitly, and you find this density of state, which has a minimum and a maximum eigenvalue given that depend on q. So as q goes to 0, is very much more data than data points than variables. So you get perfect estimation, and if the true covariance matrix has no information, it's the identity, you can actually recover exactly. So as q goes to 0, all eigenvalues become a Dirac at 1. But if you have measurement noise, if your data set is of comparable size of your number of matrices, you'll get a spreading. So how it works, so just to be more explicit, so this is what I was saying. You start with a true covariance matrix, which is just the identity. All eigenvalues are 1, so you get a Dirac at the identity. And you measure a sample covariance matrix, you measure something like this. So this is just the Marcenko-Pastur law. But you can also do it with any distribution of true eigenvalues. And when you measure, you just apply this formula. You can actually, in the case of a semicircle, you can actually write down this expression. I think it's a fourth order equation, but you can solve it numerically. And the important point is that under measurement of a sample covariance matrix, the eigenvalue distribution widens. And so you get very small eigenvalues and very big eigenvalues that are not true in a sense. And that's a problem for empirical. So if I go back to my data, you see that indeed the bulk of the eigenvalues are well represented by Marcenko and Pastur, but Marcenko and Pastur said that there should be a hard edge and that there should be no eigenvalues beyond 2. And this is not a finite size effect. Finite size scaling is like n over to the power minus 2/3. So it's finite, and n is 400. So finite size effect should be very small compared to these eigenvalues that go up all the way to 10, and then there's one at 60 or 100, basically way over there. So these eigenvalues definitely are not compatible with the null hypothesis that there's no so that there is signal somewhere in there. Okay. So one thing that we did is to say, well, let's well, you see, you can't see very well here, but if you do another type of histogram, if you do a cumulative rather than a distribution, it feels like these sort of look like they're distributed in a power law. So if we want to have a power law to the right, we tried a distribution of true eigenvalues that is fairly narrowly centered, close to 0, close to 1, but with a power law tail, and then we apply Marcenko and Pastur to that, and that fits the data pretty well. But here we were kind of brutal. It's a power law that starts at 0 and then suddenly has a large value. And actually, as well, mathematically, we're not allowed to do that. I think to use this formulation, we need to have something with compact support. But we're physicists, or worst of all, we're people doing finance and with dirty data. So we think there's some cutoff anyway, and so that's why we're allowed to do this. But you can think of this power law with a cutoff that makes it a finite support. But my point is that we could probably try different forms, and it probably doesn't matter too much what happens here. And so Jean-Philippe Bouchot recently mentioned that thought that maybe we should use an inverse gamma distribution, probably would fit just as well. Okay. Anyway, so this is what we think is a signal, and this is the data we measure, and we're facing with an inverse problem: how to go from the data we measure to the signal for real optimization problems. So try to understand, make you understand a little bit more the problems with if you optimize with a sample covariance matrix. So here I have data. So I measure data up to time t1. So I have a sample covariance matrix E1, but I want to make a decision, say optimize my portfolio, find the minimum variance weight, and then I want to apply them on the second time period between t1 and t2 and see how good I'm doing. So the E2 would be the out-of-sample period. So E1 and E2 are both realizations of a true covariance matrix that I don't know. Okay, so I can measure the in-sample risk, which is I optimize with E1 and I measure my risk with E1. There's a true minimal risk that I don't know, but I can think about it theoretically, which is that there's a true matrix C and there's a true optimal vector weights to the C, which was given by this formula. And then there's the out-of-sample risk, which is I optimize with E1, but then I measure with E2. And I can argue that since the average of E2 is C, it's the same as the true risk of my portfolio optimized with E1. So it's given by this expression where actually it's already substituted E2 with E. I'm being a bit sloppy with expectation values. When I write something like this, so that what I really mean is that the average in-sample risk is always less than the true minimum risk, which is always less than the true out-of-sample risk. And this you can argue, I won't do it here, but it's fairly simple arguments of optimality, that these weight vectors are optimum for this matrix, but they're not optimum for that one, and so on and so forth. And this is how you can say that you get these inequalities. You can also do it by convexity. Our arguments is similar, but it's fairly easy to convince yourself that the in-sample risk, which is over-optimized in a sense, is smaller than the true best risk you could get, and that your in-sample optimization does pretty bad out-of-sample. It's always worse than the best you could have done. Okay. So does that mean that the sample covariance matrix is biased? And it depends what you mean by bias. Normally we say that the sample covariance bias sample covariance matrix is an unbiased estimator of C because the expectation value of E is C. Or here I'm using expectation values for the fact that I've measured E1, and if I did it over and over again on different data sets, I use this expectation value. But when my covariance matrix is really the expectation value of Ri and Rj at some later time. So this is why I'm using these brackets for sort of out of sample. So if I take an independent portfolio, I take a weight vector that was given to me independent of my realization of E1, then E1 is an unbiased estimator. So the expectation value of the risk that I measure is the true risk of that portfolio. It's really the expectation value of the square returns of that portfolio. Okay, that's because if W is some fixed vector, or it's a vector, it could be a random vector, but drawn independently from E1, then I can separate these expectation value, and I could just put C in here. In general, if W, my weight vector, is a result of an optimization using E, then I cannot say that W is independent of E. So when I take the expectation value, I'm not allowed to separate, and I can show that this basically this in-sample risk is over optimized. It's smaller than the true risk. So E is not, the sample covariance matrix is not biased by itself, but it's biased if you use it to measure risk of portfolios that were optimized with it. So you have basically a problem of correlated noise. Okay. So, but actually with random matrix theory, you can say something a bit more precise about these inequalities, because if I go back here, for instance, the in-sample risk is, involves the matrix E to the power -1. And for a typical weight vector G, this basically, on average, it's really just a trace of E -1. And the trace of E -1 is just the resolvent at 0 with a minus sign. And with Marcenko and Pastur, you can compute the resolvent at 0, which of a sample covariance matrix related to the resolvent at 0 of the true matrix, times a factor 1 over minus q. So you can relate these things. And you can do similar computations a bit more involved for objects like this one, and you get that it's trace of C -1 or 1 minus q squared. So you can actually find precise relationship between the in-sample risk and the true risk, and the out-of-sample risk and the true risk. So the out-of-sample risk is the in-sample risk divided by 1 minus q to the power squared. So again, what is q? Q is the ratio of number of variables to number of data points. So if I have infinite number of data points, if q goes to 0, then I have perfect estimation, and I don't have all these problems disappear, and 1 minus q is just 1. And so, so I get that the in-sample risk is a true risk, which is the out-of-sample risk. The other limit where n gets close to t, so q goes to 1, well, then my sample covariance matrix, well, if n actually is larger than t, the sample covariance matrix is not even invertible. I have a certain number of 0 eigenvalues. So when I invert it to find the optimization problem, I get lots of infinity and everything blows up. So as q goes to 1, things start to blow up, and the in-sample risk goes to 0, and the out-of-sample risk goes to infinity. So it can be really bad if you're very close to that limit where the number of data, the variables is close to the number of data points you've evaluated with it. Okay. Another funny thing about these results is that the true covariance matrix disappeared. So this is a result that's independent of whatever the true covariance matrix is. You can, yeah, this is true in general. Okay. Yeah. Okay. So now I want to say, I'm saying that if you optimize portfolios using sample covariance matrix, you get pretty bad results. Can you do something better? And there have been ad hoc cleaning methods. So we've proposed one is to say that, well, the large eigenvalues clearly are signals. The bulk of them are well fitted by Marcenko and Pastur. So just put all the bulk eigenvalues to a constant and keep the large ones. So there was one cleaning method that we proposed. Another one, which I'll talk about more later, is called shrinkage, which is you take a linear combination of the sample covariance matrix and the identity, and that turns out to work pretty well, and we'll see why in a few slides. But can you make a theory of that, and of what should you do to your sample covariance matrix to improve on this problem? And you have to realize that the optimization problem we consider, we were interested in expectation value of Ri, Rj, or in a sense the expectation value of the covariance matrix. But the sample covariance matrix is a maximum likelihood estimator. It's not really an expectation value. And the only way I know how to come up with an expectation value is to use a Bayesian framework. So we're going to put ourselves in a Bayesian framework. So the question is, what's the probability of the true matrix given what I observed? And use Bayes' formula to state that. So you have a measurement process which says how to go from a true matrix to the returns that you observed, and an a priori distribution on true matrices. And this is just a normalization that really drops out of the computation. So we'll have a cleaning method that depends on our choice of prior, which is basically, and a priori, you would think that the prior is completely ad hoc. So we have a cleaning method that depends on a choice that's completely ad hoc. So are we much better than ad hoc methods? And the answer is yes, for two reasons. One is that by analytically pursuing this we'll understand better, and we'll also understand what are the assumptions behind the ad hoc cleaning methods. But also, we will see later is that we're dealing with very large matrices, and we could actually use the self-averaging properties of these matrices to actually get more. We can actually get a prior from the data, which happens because of self-averaging properties of random matrix theory, which is not true in general. In general, when you do Bayesian theory, you need to inject a prior. Where here, with some hypothesis, we can probably build our own prior from the data. Okay, so So this basically will become a matrix model. What's the probability of observing some returns given a true covariance? Well, I'm going to assume it's a Gaussian process with a variance covariance matrix given by C. So this is just this probability, which I write in this form, which is closer to a sort of a matrix model. Okay. So also what's interesting is that the individual returns that I see drop out. They only appear in this combination sum over T of Ri T Rjt, which is the sample covariance matrix. So in this point, I can forget about the individual returns. All I need is E, the sample covariance matrix. Okay, and then in order to compute things, first I'll have to assume a rotationally invariant prior, which actually is not quite true in our data. Remember, there's this market mode, which is not rotation invariant. All stocks move together, and the problem is more permutation invariant. But one thing I could do is say, if I remove this eigenvector, I know this one is clearly a signal. I can just see it, remove it, and look at in a subspace where this eigenvector has been removed, and then I assume things to be rotation invariant. That's one way out of it. Anyway, to be able to go forward with the computation, it's easier to assume rotation invariance, and that this potential, this probability distribution is in the trace class. So it's written like this. I've explicitly took out a factor A to put in front of it, and so I have a parameter to deform my my potential. So A goes to 0. My potential would be centered around the identity. Yeah, it's an important point. Is that for this to make sense, I'm dealing with variables with unit variance, and so if I don't have any a priori, if I don't know anything about the problem, the best thing I can say is that the covariance matrix should be the identity. So any reasonable prior should have from expectation value should be the identity. And so this parameter A, if A goes to 0, all my eigenvalues are centered. My prior distribution of eigenvalues are centered around the identity, and A large means I have I can have true eigenvalues fluctuate quite a bit. Okay, and so now what I need to do. The best estimate of the true matrix is going to be the expectation value of C in this matrix problem, where I have a potential now, which is given by this. So the two terms that come from what I call the measurement process, and one term that comes from the a priori distribution. Okay. So, but this potential is not rotation invariant. What this matrix E acts as like an external matrix potential, external matrix field, and breaks rotational invariant because E is in general not has some eigenvectors, very specific eigenvectors. Okay. But V0 is rotationally invariant, and so also the form of it is so there's a log, there's a C minus 1, and then there's all the terms that might come from Z0. So what kind of prior should we use? Well, as I said, the prior is actually in the data, and what I said earlier, it is when I showed that you can fit the data pretty well with a power law, says that if you this was implicitly assuming rotationally invariant. So I take I take a distribution of eigenvalues, maybe with some parameters, and I can fit the parameters to using Marcenko Pastur using the on the real data. And this would give me a prior that makes sense for my data. And this is the part that I expect might be different if you don't deal with financial data, but other data set that would come from big data, where you have a large number of correlated variables that you're trying to estimate. Okay, but but unfortunately, this prior, though, at least this one that we've written, we've actually just written a distribution of eigenvalues to come up with a potential that gives that. We haven't really tried, and it would probably be a fairly complicated potential. So we still need to go back and forth between a simple potential to lead to an analytical computation, but gives a realistic eigenvalue distribution. Okay.
Can
So
you say what you mean by priors in your data, and how that's different from other systems?
The reason is that we have a large matrix. So it's essentially the fact that in random matrix theory, you can plot the distribution of eigenvalues from a single matrix, which you can't normally if you're working in one dimension. You have one measurement, you have one variable. You don't have a distribution. Whereas if you have a large matrix, you have a distribution of eigenvalue, and it's self-averaging. So you know that looking at one sample is usually enough to give you a lot of information about the distribution. Okay, but for analytical computation, we're going to consider a very simple prior. The simplest we could come up with initially was the Wigner matrix, so a semicircle, except that we're dealing with positive definite sample matrices. So we're positive definite matrices. So the width cannot, the eigenvalue distribution cannot go below 0, and it has to be centered around the identity. So there's a condition on A, so that A should not be too large for this to make sense. But this is a potential function that we get. It's quadratic plus linear. Okay. And then you can also have a Wishart matrix. So this Wishart matrix has nothing to do with sample covariance matrix. It's just a prior. You say that the true distribution of eigenvalue is given by something like this shape, but you have a well-defined probability distribution for it, which leads to a well-defined potential, which has a linear term and a log term. So we'll do some computation with these two priors. Okay. And another, well, this was not the first prior we considered, but then looking at the literature, it's the first prior that people considered, is the Inverse-Wishart, which is you take a Wishart matrix and you invert it, and you scale it so that it still has, in our case, we need the average value is the identity. But so if you do an inverse, it has a well-defined probability distribution, which has a potential. And the potential, as you see, is C minus 1 in log. And those are exactly the two terms we had in the measurement process. If I go back 2 slides, a potential, there was a C, log C, a log C and a C minus 1 coming from measurement, okay? And if our prior is also a log C and a C minus 1, that's basically the simplest prior that we can come up with, because it has the same form as the measurement process. And it turns out if you take this prior, you can do the integral very easily. You just do a change of variable and everything simplifies. And you get a very, very easy answer, is that the optimal matrix is just a linear combination of your sample covariance and the identity with the linear combination parameter given by the ratio essentially of Q, which drive the quality of your measurement, and A, which drive the width of your prior distribution. So this, in Bayesian's estimation, this is essentially a signal to noise ratio. Here it's actually the noise to signal ratio. The term sort of E would be the signal to noise ratio. So so in front of E you have A over A plus 2Q, so signal over signal plus noise, which is really what you get in Bayesian estimation. So, okay, so and this prior is not completely crazy. It has some density of eigenvalues you can compute fairly easily. You could just do a change of variable in Marcenko and Pastur if you want, or you can compute it directly, and you get something like this, which has both as a lower edge and an upper edge. but it's more peaked at small eigenvalues than Marcenko-Pastur, and the tail is, although the tail is finite, there's a compact support, but it has a bit more of a tail than Marcenko-Pastur. Okay, so this was actually when we discovered that, we have, obviously somebody else has done it before. It was done essentially by statisticians, and they call it the conjugate prior, which is a term quite used in I think in Bayesian statistics. And they say that the Inverse-Wishart is the conjugate prior of the multivariate Gaussian distribution. So, for instance, half. I don't know if it was the first one, but that's one of the first reference we can find on this. And then later, people in finance, Ledoux and Wolf, said that given that there exists a prior for which linear shrinkage exists, they popularized linear shrinkage, and they actually found a way to estimate the shrinkage parameter from a completely different method that's actually works quite well. Okay, but I think that people have used this Inverse-Wishart for essentially for computational ease. They never we never saw any paper where they actually looked at this distribution. Does it make sense as a true distribution of eigenvalue? And another question is that the way you estimate alpha, does it make sense compared to the data? So we'll come back to these questions a bit later. But now I want to go a bit further analytically to see how much we could gain for any prior. Okay, so what we want to do is estimate the expectation value of C in our posterior distribution, which is essentially a matrix model with the external field E. Okay, so there's one method to evaluate this kind of integral is to do a perturbation, a loop expansion. So the first term for a loop expansion, you need to work at a saddle point. So you find a matrix saddle point. The matrix saddle point, well, initially very naively we thought, because there's a large n in front of it, that it would be the solution to our problem. But a matrix saddle point actually doesn't work. It's not exact. There's a large n in front of it, but there are fluctuations. Fluctuations are also very large, and so this is not exact, but it's a starting point of a loop expansion, and so you can write down the equation for the two priors we have, and in general, anyway, for any potential like this, this is just this is a matrix equation, but the only non-trivial matrix that happens is E. So if you work in the diagonal basis of E, this is a completely diagonal equation. So so you'll get that the solution C0 commutes with E, essentially. That's the important point. That the eigenvectors of C0 are the same as the eigenvalue of E. In a sense, in the diagonal base, this is just you can solve this equation eigenvalue by eigenvalue and keep the eigenvectors of E. And you get, for the Wigner prior, you get a cubic equation. For the Wishart prior, you get a quadratic equation that you can solve easily. And this is already not too bad as a starting point for as a shrinkage method or as a Bayesian estimate. Okay, so as I said, this saddle point is not exact. There are fluctuations. It becomes exact when essentially Q and A also A sort of the fluctuation in the prior distribution. Q is the fluctuations in the measurement process. So if both Q and A go to 0, then you kill all the fluctuation and the saddle point becomes exact. So you can do a limit Q goes to 0, A goes to 0, and fix the ratio of the two, and you get non-trivial results. And so other things I said that C0, the saddle point solution, and E commute, and so basically you get a nonlinear shrinkage function. Okay, and yeah. But can you go beyond that? Well, you can do a loop expansion. I'm going to skip over some detail. So if you basically, maybe one detail I want to say is that we want to write a matrix C as C0 plus something. So this is C0 plus a variable plus a matrix X that sandwich between C0 to the 1/2. This is a way to disentangle. Anyway, so X are fluctuations around C0, if you want, and so you get a matrix potential that you can expand. you have a c minus 1 term and a log term, and when you expand those, you get vertices to all order. So but you can deal with that, and the same thing with depending on your potential. Well, if your potential is a polynomial, this will stop at some order. If your potential has log terms or 1 over c terms, this will also be an infinite series. But you can keep track of all the terms. This is a matrix loop expansion, so you only have we only care about the large n limit, so we'll only keep planar diagrams. And essentially, there's a parameter 1 over q in front of all this, because now I've scaled a with q, so alpha is a over q.
So what's your Hessian when you're expanding? So you've got the south one, then you're going to compute the Hessian.
Yep. So the Hessian is basically the quadratic term here. So the k equals 2, which comes from the log and the c minus 1, and plus the second derivative of the potential. Okay, so which in general terms is kind of ugly, but for the two cases that we considered, Wigner and Wishart. Well, Wigner is just a quadratic piece, and actually Wishart doesn't have this term. So in the Wishart case, the potential no, there's a log. So in Wishart there was a log term in the potential. So the log also has a second order term. Yeah. So you get a propagator, which is how we call it in physics, and then vertices, and you can show that basically Q here acts as h bar. So like in quantum mechanics, you can do a loop expansion because which will be a Taylor series in Q. In our case, there's some higher order Q's mixed in there, but we can show that if we truncate at level k, so we have loops of order k, we can compute all the terms up to q to the power k. So anyway, so we can do this. And to first order, there's only one diagram that contributes. So the only one loop diagram is because remember we're computing an expectation value. So we're really trying to do x and then times the exponential, and then when we expand, the only term with a single loop is a diagram of that shape with a 3-point vertex, and so we can compute it. And in our prior, it's kind of ugly, but it's definitely completely tractable. But there's some important lesson here that I want to stress is that so basically the q equals 0 term, which is just our saddle point. Okay, so the saddle point was really the first term in the q expansion. Had this property that it commuted with the matrix E, and so in a sense, if you work in the diagonal base, so what it means to work in the diagonal base is I'm going to construct a matrix C hat, and essentially C in the basis of E, and so the C hat, the element I of it, with the diagonal terms, will only depend on one eigenvalue of this is just a function of EI. So the first one was just a function applied to each eigenvalue, but the second, already the first order correction has a sum over all eigenvalues. This is the only point that I wanted to make about this. So that it's not true that it's a function applied to eigenvalue by eigenvalue, but in a sense, in practice, it will be because of self-averaging properties. So if your estimate is really a sample covariance matrix, then it has some. Then all the eigenvalues are essentially related, or in a sense, this sum is over an infinite number of eigenvalues in the large n limit. So this becomes a constant function. Yeah. Anyway, but I wanted just to say that it's not true that C hat is just a matrix function applied to E. Okay, and then you have second order correction. All we did here is enumerate the graphs. We didn't even try to compute the combinatorial factor, because we were pretty sure that we would get it wrong anyway. So because there are 10 of them, so there's some 3 and 4 point function. You get 3 times 3 point function, and you have the 5 point function. So, but to show that in principle it's doable. Okay. And we've also did it on simulated data to show that this was optimal in a sense. Well, we couldn't show that numerically that it's optimal because you can't find all the possible strategies, but one strategy, which is shrinkage, you shrink the matrix with a parameter from 0 to 1, and it turns out, for instance, in this case, it's very clear that our solution with the one loop expansion is better than any shrinkage. In this case, it's essentially the same as a shrinkage with a very specific parameter. But numerically, we never found an example where we could do better than our theory, which is kind of a hint that it's optimal in a sense. But this, of course, is numerics on, we know the prior, so we generate matrices compatible with our prior. So we're cheating in a sense. Okay, but so I have about 10 minutes, so I have to speed up a bit. So I want to say that another technique that we can use to solve this problem is to do not a saddle point, a matrix saddle point, but an eigenvalue saddle point, which in this case would be exact. The problem with the eigenvalue saddle point is the problem with this term here. So remember, there was a coupling between C minus 1 and E. So this is just the Harry-Chandra-Edukson-Zuber integral between E and C minus 1. And this so there are some large and limit results for this, but the ones that we've tried are very complex, very complicated, and so we couldn't use them to solve our problem. But so this is also, I mean, I'll try to discuss with people after my talk if some people have some ideas how to make sense. Basically, all we care about is the n squared term. So this integral here behaves like exponential minus n squared times something plus I order corrections. We only care about this function here, and so we found the work of Matutsin, which Guionnet and Zeytouni have formalized. But we can go very far with that. So if people have ideas of or more recent results on how to deal with something like that, would be very useful. So in order to get somewhere with this technique, we have to solve a very simple, much simpler case when E is proportional to the identity. So if I do that, if I say that E is proportional to the identity, I'm looking for a function of E. So I say, well, the only case I can compute is when E is proportional to the identity. I'll get some analytical results. In practice, it's completely wrong because E is a sample covariance matrix, and it would extremely almost impossible that it be proportional to identity. But initially, we thought that the solution would just be an eigenvalue by eigenvalue function, and if that's the case, then we could use this. But it turns out that we saw the one loop expansion that breaks this assumption. But nevertheless, these are analytical results that can be useful. They can be useful to check the perturbation theory, and maybe they're the starting point of some other expansion. Okay. Anyway, so we solved this using the techniques of Brezin, Edukson, Parisi, Zuber. With some slight differences that in the BIPZ paper, they looked at polynomial potential. We actually have a log and some negative powers, but really what's important is that the derivative of the potential is a polynomial, or it can have terms like 1 over z squared, 1 over z, 1 over, and you can just apply the same techniques. Okay, so we slightly extend. Also, the other difference with BIPZ is that we're dealing with real symmetric matrices, not Hermitian matrices, but so. Yeah, exactly. Yeah. So, but basically, all that changes is a factor of 2. So, but we need to keep track of. We can't use their results exactly. We just have to keep track of factors 2 that are slightly different. Yeah. So basically, in our case, beta is 1 because we're dealing with real data, real matrices. Nothing's complex except when we play the resolvent in the complex plane. But no, we're dealing with real matrices. So anyway, so we get an expression like that where we know the powers of Q's. And basically, this, in BIPZ, they have regularity condition at infinity. We also, because we have poles like 1 over z, 1 over z squared, we also have regularity condition at 0. But it's essentially the same problem. And we find, well, so for instance, in the Wishart case, you get this type of equation, you get fourth order equation, but so you can't be completely analytical about it, but you can say, well, there's a solution to this fourth order equation, and then you can write the resolvent. Now, given that I assume that E is proportional to the identity, there's no eigenvectors in all the there's no matrices anymore in this problem. All matrices are proportional to the identity, so so I can actually what I'm saying is that C hat will be proportional to the identity. What's the constant in front of it? I need to compute the trace of C hat. And to know the trace of C hat, I can just look in the resolvent. It's a Z square term. 1 over Z square term is the trace of C hat. So I can just read off that my expectation value. I can read it off from this term. Okay. So just want to say that that at least it allowed us to check that the perturbation theory made sense, and it gave the same results to the same orders. Okay. I want to go very quickly on numerics. So basically, there's a numerical way of doing this, which uses rotational invariance. Maybe the best way is to show it on an example. So to check that our numerical method worked, we took the one case that we can solve exactly is the Inverse-Wishart. Inverse-Wishart, we know the Bayesian estimator is linear. So so we can basically the technique is a Monte-Carlo in a sense, and you generate a random matrix from your sample. You generate a sample covariance matrix from that matrix. You try to match the eigenvalues, and you do that over and over again. You get a cloud of points, but the solution is the average over this cloud of points. And it turns out to, we kept the points, the Monte Carlo points, to give you an idea of the errors, but the technique says that you should take the average for a given eigenvalue here. So you measure an eigenvalue 3.5, you read off what you should shrink it to 2.5 based on the blue curve, which is just the average of the dots. So that's the numerical technique in a sense. Okay. And then we can compare the different techniques, the analytical solution that we have with the numerics. Don't want to go, works well. But one point I want to say is that these priors they give shrinkage techniques that are concave. So you shrink more high eigenvalues than low eigenvalues. So if you see that as you get higher and higher, if you measure a very high eigenvalue, this technique says if you have a Wigner prior, you say don't trust it, get it closer to 1, and that's because the Wigner prior doesn't have tails at all. It's a semicircle identity. So if you see a very large eigenvalue, it's probably noise. So you want to shrink it back to the center, closer to 1. But so this is why these priors are not very realistic in our data. So Wishart has the same characteristic; it's concave. Inverse-Wishart are really linear, which is better than these. Just want to say that you could actually do everything numerically. Forget about all the theory, and say take your data. This is again the same curve again of true eigenvalues. So these are the eigenvalues the eigenvalue distribution that if we inject in Marcenko and Pastur fit the data pretty well, and so now we have a prior that's just a numerical prior, but nevertheless we can do the Monte Carlo on this numerical prior, and we get an estimate, and it's the blue curve here. And what I like about this blue curve is that asymptotically it almost doesn't shrink the very large eigenvalues because our prior has a fat tail to the right. So if you see a very large eigenvalue, it's compatible with your prior, so you keep it. Whereas it has no eigenvalues below a certain point. So eigenvalues that you observe here, you don't trust them at all. So it has the opposite convexity of the Wigner and Wishart prior. Okay, and here's just comparison with the two ad hoc techniques that we're doing before, which is eigenvalue clipping, which is you just say you keep a certain eigenvalue up to, say, in this case, up to eigenvalue 3.9, you keep the eigenvalues, and if they're below 3.9, you put them all to a constant. So this would be the green curve. And then linear shrinkage is just a linear function of what you observed. And this is the blue curve. So we haven't had time yet to compare this with, on real data. So this is the result of the optimal, but we haven't checked out of sample. On real data, many other things happen. The data is non-Gaussian, and also there's no such thing as a true covariance matrix. The correlation between stocks probably changes over time, and so it's going to be much more messy than on numerical experiments. But we need to do that. Okay, so yeah. So basically, my conclusion is that this out-of-sample problem can be written in a Bayesian framework. That one-loop expansion gives actually a pretty good result for simple prior. Okay, and there's a numerical procedure to do all that. But I think it's always important, even if you have a numerical procedure, to do a lot of as much to go as far as you can analytically to really understand the structure of your problem. Okay, and so the first open problem that we need to do now is to look at real data. So look at and see how it's performed on real data. So an important open problem is, can we go further with the eigenvalue saddle point, and for that we need to use some workable limit, large n limit of the Harry-Chandra-Itzigson-Zuber integral, and there's some extensions, because we know that the data is non-Gaussian. So but we use the measurement process that was Gaussian. Can it be extended with student multivariate? Probably yes. And also we know that the real data is not rotation invariant. There's at least a market mode which just has permutation invariance, not rotation invariance. But can we say something about these? Yeah. So that's all I wanted to say. Thank you.